So just to re-emphasize what I said at the end of the previous clip, if the exact meaning of a limit is not perfectly clear to you right now, don't worry, that's completely normal. The explanation I gave is vague, for starters, but that's all we're shooting for. Right? The main purpose of this section is just to give you one reason, at least, for why you should care about the slopes of tangent lines. And for now, that reason is just going to be that we can use them to define instantaneous velocity. Ultimately, this section is the motivating section for a limit. And that's what Chapter 2 is about. We're going to start in the next section by completely developing limits from scratch. We're going to start over with the basics, and we're going to go through it in detail. But for those of you that are interested, I do want to at least show you the formal definition of a limit. This is an alternative phrasing to what is commonly referred to as the epsilon delta definition of a limit. It's quite technical if you want to work with it rigorously, but it is straightforward to state. So we're going to take advantage of that now, take advantage of the opportunity right now. Because if you ever go on to take a more advanced course in calculus, you'll likely work with it. So it's good to have seen this at some point. So this is the formal definition. For a general function f, so you could have any function, we use the limit notation, which is right here. And so that's what goes here, the limit notation. Let's add that. And let's read this out loud, how you would read this in English. You'd say the limit as x approaches a of f of x is equal to L. So if you were to say this out loud and somebody was writing it down as you said it, that's how you would say it out loud. You'd say the limit as x approaches a of f of x is equal to L. And if you say that to someone who's familiar with calculus, they'll know what you mean. Now, what does it mean exactly when you say this, though? What does the notation mean? Well, this is the definition. I put a little bracket here to isolate the statement. This is the statement that you are claiming when you write this. Okay, and you're saying that you could force the values of f of x, so the output values from the function f, to be arbitrarily close to L by choosing the values of x to be sufficiently close to a. So what does that mean exactly? It means if you want to make f of x really close to L, no problem, you can do it. But the cost might be that you have to force the values of x to be really, really close to a. And how close will you need to make the values of x to a? Well, it depends on how close you want the values of f of x to be to L. But this statement is saying that you can always do it. That's what the word arbitrarily means. It means you can make the values of f of x as close to L as you could ever possibly like, as close as your whim would ever desire, right? That's what it means to say arbitrarily. But whatever desired level of precision you want to force f of x to be close to L in, so the narrower the window around L that you want f of x to lie within, the narrower the window around A that you're going to have to force the values of x to lie in. So that's the use of the word sufficiently here. Okay, so just to finish off, this last definition really summarizes everything from this section in a nutshell, so it's actually a really good place to end off. Okay, so we've talked about the position function, s of t, and we use that definition, we use that function to define the instantaneous velocity at some point in time, which we labeled t star. Well, now that we've finished laying out that definition, the need for the variable t star has kind of vanished. So we can simply just define the velocity function v of t to be the instantaneous velocity of whatever object. Remember, when you have a position function, you have to have an object moving in one dimension. So that's all laid out in the background. But the velocity function, v of t, is just defined to be the instantaneous velocity of the object at time t. So the name of this function is the velocity function. I already said it by accident, but as you can see, that's what it's called. And really, based on what we did on the previous page, the work we did over here, we could just basically recycle this idea, basically just rewrite this formula, but drop the t star and just replace it with t now, because it works at a general point in time t. There's no actual need to use the symbol t star anymore. So that's why we can write down this following formula for the velocity function. And you could argue that this really is what the velocity function is. This definition that I wrote here is really just telling you what the velocity function gives you. But if you prefer to work in terms of a formula to compute it, you can use this. So v of t is just the limit as h goes to 0 of s of t plus h minus s of t, all divided by h. So that is the velocity function. So we've got a position function, s of t, and we've got a velocity function, v of t now. Okay, so that is the end of 2.1, and like I said, we'll basically start over from the very beginning now with limits in the next section. This whole section, this formula is really to motivate the idea of a limit and tell you why you should care about them.